Welcome to another exciting educational video brought to you by Chrysolite Tutors. Today we'll be looking at MTH 105, Mathematics for Management Science Part 1, and we'll have Unit 3, Vectors and Complex Number. It promises to be an exciting topic covering some basic concepts on vectors and complex numbers. In this video, we'll look at the vectors, types of vectors, um, unit positional vectors, subtraction, addition of vectors, multiplication of vectors, position vectors, unit vectors, and complex numbers. We'll look at the properties of imaginary numbers, algebra of complex numbers. We'll also see scalar multiplication in complex numbers, multiplication of complex numbers, division of complex numbers, absolute value or modulus of complex number, and lots more. So please sit tight and stay tuned to the end of the video so I can get all the concepts. If you're not subscribed to our channel, kindly subscribe to get more content. So sit tight. So before we move into vectors properly, it's very good for us to understand what scalar is. Scalar are quantities that have only magnitude. Understand? It just specifies numbers. So are quantities which specifies numbers, or I can call it magnitude, specifies numbers. You understand? And it measures in terms of some chosen units. You understand? But does not have any specific direction. So that's the keyword. It specifies numbers without specific direction. Examples of scalar is examples include speed. Speed is just like you have 5 meters per second. Then energy measured in joules. Mass is measured in kilogram. Okay, I'm just putting that for mass. Density is also another form of scalar. Time is form of scalar. You see, this just measures number and it has unit. It just measures the magnitude as a unit. But vectors, on the other hand, is a physical quantity which has magnitude as well as direction. Example is velocity. See, so examples of vector. Examples is velocity. So this specifies both magnitude and direction. Acceleration specifies both magnitude and direction. And displacement, when you say something moves so and so meter due east. So these are examples of vectors. So for the types of vector, we're not going to deal with the types in this particular course. It's beyond the scope of this course, but it's just interesting for us to know the types. So I have three vectors. Number two, I have time and time-related vectors. Time and related vectors. All the vectors related with time. You understand? Then we have point located vectors and position vectors. Point located vectors, and finally position vectors. So as we progress in this particular topic, in this course, we'll be making use of this term even while we discuss. But I want us to see how we represent vectors, vector representation. How do we represent vectors? Okay, so I will draw the diagram on the board. So we have vector representation on the board. This is your Cartesian plane, your x and y axis, positive y axis, positive x axis. And vectors are actually lines showing direction. So this line is showing this direction. A and B is showing direction going upwards in northwest or northeast direction. Okay, so this is the symbol. A, B, then a bar at the top, or small a and a bar at the top. That's what we use to represent vectors. This one is going up, this one is coming down. That's the difference. So mathematically, it can be proven that if I have a vector, a bar here, uh, uh, is equals to a if a is greater than 0. And then vector a is equals to 0 if actually a is equals to 0. And it's also proven that vector a is equals to minus a if a is equals to negative or less than 0. Okay, so it's just, the thing is that vector has a magnitude in it, which is this number here, So I can try to represent this one as 5. You understand? 5. And this one as 3 if it's different. So this one is going up, this one is coming down. There's also algebraic summation of vectors, or division, subtraction of vectors. So vectors can be added, actually. That is what we are saying. So we just dive onto vector addition. If I have a vector going in this direction, for instance, this is AB. At this point, it changes and goes like this. And this is BC. So there are two vectors here, or two movements. This first direction and second direction. Total resultant movement for this kind of vector is, this is C, sorry, is AC. So this is the resultant movement, AC. So if I call this one vector A and vector B, you understand? Then vector C is the resultant movement. So vector A plus vector B is equals to vector C. Normally, this vector C is gotten by the sum of vector A and B. And that sum is actually using the cosine rule, but it's not just what we'll be looking at now. We'll look at it later. But this kind of thing is applicable to where you have a movement. For instance, now a vehicle is moving from one part to another part. It moved, let's say it moved, this is the starting point of the movement of the vehicle at point A. It moved maybe like 50 kilometers due east. When you say due east, this is the cardinal point. This is north, west, east, and south. If it starts from here and move due east, that means it's moving towards your right, like this, moving like this, due east. Now it comes to this point and moves on maybe like 30 kilometers northeast. Northeast. So this direction is northeast. Northeast is like 45 degrees from the normal. So it is used, they will not say, will not be asked to calculate the resultant movement. The resultant movement is not actually this plus this. It is just the whole of this. And that can be gotten through some cosine or sine rule application. Okay, so but we just want for us to appreciate what is with there. We'll dive into subtraction of vectors. Vectors can actually be added. Like I said, if I have a vector that is a movement between A and B, for instance, A and B, and B and C, you understand? B and C. So vector AB plus vector BC is equals to vector AB. AC, sorry. So look at it. Movement between here and here, and here and here. If you add the two of them, it will give you just this. So this is addition of vector. So subtraction, on the other way, is when the vector is moving. If the body is moving, in an opposite direction. So you can actually have a vector maybe after it has moved like this, like this, like this. Any movement going backwards, like this movement that is going forward, like this. Everything here is addition. Here, addition. Understand? But when it's moving, if this is A, this is B, and this is C. When it's moving backwards, C will now become subtraction. So we will see what problems, even as we go further in this course, where there is division, subtraction of vectors. Okay, so for multiplication, going by the laws of addition of vectors, a plus a is 2a. For addition, if I say a plus a, that's vector, is 2a. That is algebraic sum. Algebraic sum. So if we decide to now add continuous, for nth, then it now becomes a, 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 continuous. If I decide to put my bar like this, then the final answer will now be NA. This N represents the number of A's that I'm having there. That is if the vectors are equal. If they are equal. So, for multiplication, we just simply do a multiplication of the numbers that represent that vector. Okay, we're not going to be diving much on vectors because when we start doing the problems, it's going to be easy for us to apply them. All right. Okay, so we have position vectors on the board. Position vectors. So position vectors have to do with you trying to place vector in the position in the Cartesian plane. Again, this is the Cartesian plane x and y axis. If I have a point on this plane, this is a two-directional plane. So if I have a point on this plane, point P, for instance, point P, you agree with me that point P has a reference to the x-axis. So if I trace this down, there's a value that it will have here on the x-axis. Let me call this value A, for instance. Okay, and if I trace it to the y-axis, there is a value it will have B. So with position vectors, we can actually represent P in this form. P is equals to AI plus BJ. Okay, BJ, where I in this case, where I is actually positioned in the x-axis or x-axis. Let me just call it x-axis. X-axis position, x-axis, and the J is the y-axis. So this actually axis, you understand? But the A is the value of the y-axis, or value of P on the y-axis. Value of P, because P is our reference, on x-axis, and B is the value of P on the y-axis. This is simple enough. So look at it this way. If, for instance, now we have a point P, and P is 5 on the y-axis and 6 on the x-axis. What this means is that if I want to represent it in positional form, P is actually 5i plus 6j. This is how P is represented. So from here I can read that this is the x-axis component and this is the y-axis component. So I can say that P is having value of 5 on the x-axis and having value of 6 on the y-axis. Now, if I'm asked to calculate what we call the magnitude of modulus, I'm introducing a term here, magnitude of modulus. Magnitude of modulus is actually a resultant number that can replace these two numbers and have the same effect of that number. So magnitude or modulus is the resultant of a positional vector. Okay, now this is just a simple definition, but when they say for this particular case now, find the magnitude or modulus of this. Magnitude will be equals to the square root of the A part square plus the B part square. So for this particular case, the magnitude of modulus represented like this. This is how it's represented. Is equals to 5 square plus 6 square, or square root. So the magnitude of modulus is square root of 25 plus 30. So P modulus is equals to this and this is what? 5, 5. So root 55. So that's the answer. If you express root 55 to the exact value, you will get the magnitude or modulus of that particular vector. So if, for instance, we say we are giving example, maybe in your TMA or in your exams, you say find the magnitude of the following. Find the magnitude of the following. Okay, are you following? Number one, we're given a positional vector 3i plus 4j, and number two, we're given a positional vector 5i plus 7j. Okay, so these are two positional vectors. Simply put, this one represents the x component and this represents the y component. Okay, so for magnitude of this vector, I'll just say square root of 3 square plus 4 square will give me 3 times 3 is 9 plus 4 times 4 is 16. 25. If you add the two of them, 5. So this one, number one, is 5. Number two, square root of x component is 5 square plus y component is 7 square is equals to square root again. 5 square is 25 and 7 square is 49. So if I add the two of them, 9 plus 5 is 4. 4 plus 2 is 6. Plus 1 is 7. 74. Okay, so if you find the square root of that 74, you get the modulus or the magnitude. So you can do more. You have more examples in your material. Okay, so we are looking at unit vectors. Unit vectors are actually vectors that expresses the positional vector to the modulus. Okay, so by way of formula, a unit vector is equals to the positional vector divided by the modulus, or what do you call it? You call it the magnitude. Okay, so if for instance, I say find the unit vector of, so I'll just do one example quickly of A. Number one, A is equals to again 4i plus 3j. Now note again, this component is the x component and this one is the y component. The I is telling you that it's x axis and the j is telling you that it's y axis. The 3 before the I is telling you that A position is 4 units away from the zero margin or the zero origin, and that's on the x-axis, yes. And the 3 here is before the j is telling you that A is 3 from the origin on the y-axis. Okay, now let's say find the unit vector. The first thing you do is to get the modulus. So modulus or the magnitude. Please let me, because sometimes they can use that word find the modulus or find the magnitude. They are one and the same thing. Modulus is equals to the square root of 4 square plus 3 square. 4 square is what? 16. 3 square is what? 9. All square roots. Then 16 plus 9 is 25. All square roots. And square root of 25 is 5. So the modulus of this particular positional vector is 5. Now to find the unit vector. So I'm going to divide this one by 5. So I will say 4i plus 3j all over 5. Of course, you can split it into two components. The same thing as saying 4 over 5i plus 3 over 5j. So this is the answer. This is the unit vector of this particular vector. So you see the definition. Just divide the positional vector that is given by the modulus. And we have been told how to find positional vector, modulus. Just divide it. Every other thing here is arithmetic. If you know the definition, just every other thing here is mathematics. Okay, so we'll just do one more example quickly, and we'll move on to complex numbers. Okay, so if I say find the unit vector of C is equals to 5i plus 3j. Again, this 5 is telling us that object C is 5 cm. Okay, let me put it. Not 5 cm, please. Y axis, X axis. So what this one is telling us is that position of C is 5 here. Let me use a broken line. If you measure it to this place, it's 5. If you measure it to the y-axis, it is 3. That's what this thing is telling us. That was telling us. That these are positions on the Cartesian plane, where I is the x-axis, this is 0 mark, x-axis, and j is the y-axis. Okay, so the modulus of this is the square root of the summation of 5 square and 3 square. And modulus or magnitude is 25 plus 9, because 5 square is 25, 3 square is 9. Add the two of them, I get 34. Right? Right. So this is the magnitude. So if I now come here and now say the unit vector is equals to 5 over root 34i plus 3 over root 34j. Okay? Okay, so the next one we're looking at is complex numbers. So complex numbers come from the fact that there are some numbers we cannot resolve fully. If, for instance, we have x squared plus 1 is equals to 0, to find 1, x squared is now equals to minus 1. Why? Because plus 1 we go to the other side and becomes minus 1. So to get x, you take the square root of x, or both sides, sorry. So I now have x is equals to square root of minus 1. Now this number cannot be resolved because I cannot get the square root of minus 1. So because of this state that we are stuck in, we can say let us represent this by I or j. Some textbooks will use j, or we can use I, small I. So I actually is root minus 1. So this is a complex component. It's complex. So sometimes we represent complex numbers in this form, a plus bi, where this is the real part and this is the complex part. So this is the real part and this is the complex part. But this is what makes it complex. Understand? Now, there is this powers of I. So we know from this basic form that I is root minus 1. Now, I square is the square of this. Understand? So by the time you remove the square root, you will have 1. So, sorry, minus 1. So I square is minus 1. Why? How? Look at it. I square is equals to minus 1, root minus 1, then square. You know that root minus 1 is something as minus 1 raised to the power half times 2. This and this are the same thing, right? So this will cancel this. So my I square is minus 1, and the I cube is having I square and I. You understand? And I square is given as minus 1. So I cube is equals to minus 1I. So I have this, I have this, and I have this. And finally, I raised to the power 4 is equals to I square dot I square. And I square is minus 1, I square is minus 1. So I raised to the power 4 is equals to 1. So it is a circle. So I have these standard forms. I is root minus 1. I square is minus 1. I cube is minus I, because if I say minus 1I, it's thinking I say minus I. And I to the power 4 is 1. So if you know this one like this, you can recycle powers of I. You can recycle powers of I. In that, even if I have I to the power 7, for instance, I know that this is something as saying I raised to the power 4 and I raised to the power 2 and I raised to the power 1. This is it. Because 1 plus 2 is 3, 3 plus 4 is 7. So these are already in standard forms, where this one is 1 times this one is minus 1 times this one is root. This one is just I. You understand? So finally, I7 is the same thing as saying minus I. So you can recycle it. You can recycle this. Okay, so having known the power of I and the concept of complex number, we'll dive into the different things we do with complex number. We'll quickly go into addition, we'll see properties, algebraic addition of complex numbers. If, for instance, you have this on the board, quickly, this on the board, let's say let Z1 be A plus B I, and Z2 is equals to A2, this A1, B1, A2 plus B2I. So if we are to find the sum, Z1 plus Z2 will now be the whole of this A1 plus B1I plus A2 plus B2I. Okay, so we can now add the real parts. We add the real part A1 plus A2, then we add the complex part B1 plus B2, then I. So this is how we can resolve it. So if we say example, let's say they say we should find Z1 plus Z2 if Z1 is equals to, let me put some numbers to it, 3 plus 2I, and Z2 is equals to, what do I use? Z2 is equals to 4 plus 3I. 4 plus 3I. Okay, so now at this point, I will say Z1 is what? 3 plus 2I, then plus Z2 is 4 plus 3I. So collect the real parts, this and these are the real parts. 3 plus 4 plus, collect the imaginary parts, 2 plus 3, then I. So 3 plus 4 is 7 plus 5I. So this is the answer. That's the answer. 7 plus 5I. Okay, let me do another example. So if Z1 is equals to 3 plus 2I and Z2 is equals to 4 plus 3I, find Z1 minus Z2. So Z1 is 3 plus 2I, then minus Z2 is 4 plus 3I. So we'll do the sum, this and this, 3 minus 4, then plus plus 2 plus 3i. That's, you are doing this and this. Okay. Okay. So it's going to be minus. Why? Because there's a minus here. Minus, when this one multiplies this one, you call minus. All right, so it's simple enough. The 3 minus 4 is minus 1, plus 2 minus 3 is minus 1, so it becomes minus I. So this is the answer. 1 minus 1 minus I. All right, so we're going to break this video into two. At this point in time, we'll stop here for the end of the video. So we'll have a second part where we'll do the concluding part of this topic. We are still in complex number. So I hope this video has been informative for you. I'd like to thank you for viewing.